Well, good afternoon. We are back to our workshop. First of all, thank you very much, Nalini, for accepting our invitation. I would like to say some words about Nalini. Nalini is professor, University of Connecticut, USA. The research interests of Nalini include time series analysis, software reliability, and the statistical analysis in many areas. Nalini has many publications, including two books, and also I would like to mention that Nalini is the co-editor-in-chief of the International Statistical Review. Nalini, please.
Thank you very much, Mario. Thank you very much for inviting me to speak at this workshop. It's my pleasure to virtually be in Brazil. I was just saying before in our conversation that I loved visiting Brazil, and I have a lot of friends in different parts, Rio and the Sao Paulo area and Carlos. And Marino and Katiani visited UConn very recently. Unfortunately, it was during the COVID time. Nevertheless, we got a good bit of work done. So there's a lot of Bayesian connection, and it's my pleasure to speak here. And I look forward to suggestions, comments, as I go through and present what I want to do today. So what I wanted to talk about was a cohesive framework for modeling time series of counts. As we discussed, this may not be the only way of doing this. And at the end of my talk, I'll actually show some alternate ways of looking at it. But nevertheless, what I want to show here is a Bayesian framework for modeling vector time series of counts, both using MCMC as well as using INLA, using this package R-INLA. So let me get through and show you what I'm trying to say. So I'll first introduce, then I'll show you some models for count time series. Specifically, I will talk about a hierarchical multivariate dynamic model for a vector time series of counts. And I will talk to you about the distinction between that model. So in the HMDM, what we do versus a second model framework, which I call the level correlated model. The primary distinction between these two models will be that when I talk about a multivariate dynamic model, I am thinking that my response vector, which is going to be a time series of counts, right? I'm going to think of a conditional sampling distribution for that vector to be a multivariate count distribution. For example, I will be looking at the multivariate Poisson distribution. So the sampling distribution itself is a multivariate distribution. Versus when I think about this level correlated model, what we are trying to do is we are thinking of each component of my multivariate count vector is conditionally univariate Poisson, and any dependence that exists between the components of this count vector is going to be handled at the next level through a multivariate Gaussian construct. And so this will be the sum total of this presentation. If notations or something are not clear, please feel free to stop me in between. So I don't need to possibly motivate this, because I think pretty much a lot of us are aware that more and more in different domains, as we enter this data science era, we need to build models for multivariate time series of counts. They come very often, and once they become time series, we say that we have to take the history into account when we do the modeling. And oftentimes we have a lot of exogenous predictors that the scientist or the application person throws at us and says, let's try and use these predictors. Now, when we build models, the focus of this talk is on how do I incorporate, not that I'm saying the temporal dependence we should certainly incorporate, but we are going to also have to incorporate any dependence that exists between the components of this time vector, of this count vector. Now, one could say, why cannot I model univariate time series separately? Yes, you can. And then, but of course, you are not incorporating the dependence. So one way is to see whether we can build a model that can incorporate the dependence. And then, of course, you can compare these models with building separate univariate models in practice. And if the two give you the same level of predictions and so on, then in future, you don't have to kill yourself building these multivariate models. You might as well build univariate models. But at least this exercise must be done once in the domain that you are interested in. I would, if you guys have not already seen this, I would like to point you to this very nice review of multivariate time series of counts, modeling in the Bayesian context. This is by Refik Sawyer and D. Zhang. This is in this Wires Computational Statistics Review Journal 2021. Very nice review to look at. The other pitch that I want to make, if you're interested in discrete value time series in general, is the CRC handbook that a bunch of us co-edited. As you see, the editors are Richard Davis, Scott Holen, Robert Lund, and myself. So it has several chapters that are grouped into 5 sections, and people that are especially interested in frequentist and Bayesian constructs and modeling for discrete value time series, you may want to take a look at some of the articles here. Okay, so once again, here is a concise statement of what I would like to talk about. In different disciplines or situations, the number of time series, n, so I'm thinking about many time series, many customers, many physicians, many locations. The number of time series, n, the time series length, t, the number of predictors, let's call that k, as well as what the questions of interest will be different, right? I worked in transportation engineering, I worked in finance, ecology, yes. So the questions that are of interest are different. In some cases, it may be the effect of exogenous predictors. So what are the risk coefficients? In others, the question might be purely prediction, right? Give me the best model so that tomorrow I can understand what's going to happen. So we are going to build a Bayesian modeling framework, which also scales well as some of these dimensions increase. The two approaches, like I mentioned in the introduction, are this hierarchical multivariate dynamic models. I'm going to leverage in a sampling distribution, which is a multivariate count distribution. And I'm also going to use Markov Chain Monte Carlo. And the second one is a level correlated model where each component of the count vector is conditionally a univariate distribution. The dependence comes at the latent Gaussian process level. And I'm going to be showing how we used the R-INLA approach, which is an approximate Bayesian approach for model fitting. So when I think about hierarchical multivariate dynamic models, let's set some notation. So I'm going to call this vector y sub it to be an m-dimensional vector. So there are m components in my count time series. So it's an m-dimensional time series of counts on n subjects or time series or locations at times t going from 1 to t. Okay, so can I make t, ti? I don't know. We have only taken the regular time series. We have at this point considered regular time series of equal length. So one example from ecology, for example, that we have done using this MCMC approach comes from this, ecologists want to model patterns of the occurrences, how many counts of some snail species in this forest in Puerto Rico. And they have a bunch of topographical and environmental covariates, including an intervention in the presence of a hurricane that came. And they are mainly interested in understanding what is going to happen to the patterns of the counts of snails over time. And this is the study that we did. Mike Willig is an environmental and ecologist at UConn, my university, and we used his data and his problems to address this issue using this HMDMs. And this was a paper in 2014 in Statistics and its Interface. So basically, how did we, when we set this up, HMDM, what exactly are we falling back upon? We are, in fact, looking back to papers from very strong Brazilian Bayesian statisticians. So looking back to the JRSSB paper on hierarchical dynamic linear models by Gammerman, Dani Gammerman, and Elio Migon. And Dani also had another paper, Landem and Gammerman in the CSDA in 2000, where they used multivariate normal, matrix variate normals rather than multivariate normals. This is one area, right? So the response vector is Gaussian, and your state equation is also Gaussian. And so this is, what do you do when you have a hierarchical? So you have many, many sets of such observation and state equations. So this framework addresses that, and they will call that hierarchical dynamic linear models. Okay. The second direction is to go away from normality and to be able to handle things like counts or incidences. So if you stay within the exponential family and you think of doing something like the GLIM, but then you have things that occur over time and you want to have dynamic evolution. A very nice paper that I like a lot is the Biometrica paper by Dani, where he introduced this so-called DGLM, Dynamic Generalized Linear Model Framework. Now, we have extended some ideas from there. The modeling is slightly different, and we have a paper in this handbook that I spoke to you about. So if you're interested, you can go take a look. So there is an expansion of this DGLM to the hierarchical framework as well. So we included a hierarchical setup and also modified the modeling steps a little bit. So this is one paper that we have. So let's get down to some details. So we again have this m-dimensional time series of counts, several of them, right? So I goes from 1 to n, t goes from 1 to t. Now, what are we going to do? We are going to do Bayesian inference. We are going to put a multivariate count distribution. The count distribution is going to be not just an m-variate Poisson distribution. It is going to be a finite mixture, so with H mixans in it. So it's going to be a finite mixture of m-variate Poisson sampling distributions. That's going to be the mechanism by which we model. And then we are going to do the parameter estimation using the Gibbs sampler with some modifications. So in this setup, the observation equation is going to have, it's going to say YIT given the relevant parameters is a finite mixture of m-variate Poissons. And I'm going to tell you what that form is in the next slide. But then let us say that the coefficients that are existing in the right side of that observation equation are unknown parameters beta, right? Now we can model these betas as subject specific and time varying. So it's going to be beta sub IT. Then similar to the Gammerman-Migon paper, we are going to have a structural equation where this beta IT is going to be aggregated to simply a state vector gamma t. And then there is going to be a state equation that evolves the gamma t in a linear Gaussian Markovian way. So that is going to be, this is how we kind of bring in hierarchical, we bring in the count nature, and we also bring in like the underlying state space formulation that we are used to. Here is a quick reference to the kind of things that I'm going to talk about on the next slide. The I'm sorry, this must have been 2005. The first paper in Stat and Computing is a 2005 paper where they introduced this covariance structured multivariate Poisson, which is an easy multivariate count distribution. Then they extended this to the mixture of Poissons. And then this is another nice review paper by Dimitris Karlis in our DVTS volume. So let's define this M-variate Poisson distribution. I will say that Y in general, I've taken out all the I's and the T's. So Y equals AX follows a multivariate Poisson distribution with some Q-dimensional parameter vector, right? So in some sense, if I want to define the multivariate Poisson distribution, I am going to give this format, okay, as a function of Q. We have to now understand the connection between Q and M soon. We are going to say that there is a Q-dimensional parameter vector, and I can write the PMF, the probability mass function of this in the following form. This is a form that was given in a 1960s paper, in a JASA paper, okay, where for each R going from 1 to Q, we have this being a univariate Poisson. But then, you know, Dimitris Karlis argued that this is not very easy to handle in practice. Therefore, we have this two-way covariance structured MVP, which comes in this 2005 paper. So basically says, let us take that A and we divide it into two parts, A1 and A2, partition it. A1 captures the main effects and A2, so there are M main effects, and A2 has an M times M choose 2. Right? This captures the two-way covariance effects, as they called it. Okay, so basically, we are going to simplify the Y equals AX by approximating or writing this A as two portions. One captures the main effects and one captures the two-way effects. And we correspondingly split the lambda, which is a Q-dimensional vector, into two parts. So for example, if I take M equals 2, so Y is a bivariate count vector, we will need 3 independent Poisson random variables. So Q is going to be M plus M choose 2, right? So we are going to take Q equals 3 independent Poisson random variables. Y1 is written as X1, the first Poisson, plus the third Poisson. Y2 is written as a second Poisson plus the third Poisson. Okay, in which case, this is what this A matrix will look like. This is going to be that identity IM matrix that we talked about, and this is going to be the second part. Then the joint PMF of Y1 and Y2 can be easily written out, yes, in this form. You can, I could have written it out for M equals 3 as well. Our paper has all these details, but I'm just going easy here. So the whole idea is that if we have an M-variate Poisson, I can use this construct. And I can write this as a linear combination of some independent Poisson random variables, Q of them. And each of those independent Poissons will have its own lambda. So I will end up with lambda 1 through lambda q. So now you can go to the next stage of the log linear modeling. Before we do that, let us look at the moment properties of such a thing. So we can easily show that the conditional expectation of Y given lambda is A lambda, and the conditional covariance is A sigma A transpose, where sigma is going to be a diagonal with lambda 1 through lambda q. Remember, lambdas are all positive. These are the means of the independent Poissons. Therefore, clearly, and A is going to be just this matrix of ones and zeros, right? So this covariance cannot accommodate negative associations among the components of Y. And why is that important? Think even about the snails example that we said. Let us say there are two species of snails that live in the same tree, bush, shrub area. Now, there could be a positive dependence if all the environmental conditions support both of them, right? So it is possible that there is a positive dependence, both grow simultaneously, or in other cases, if one type of snail utilizes some resources that the other type of snail therefore loses, there could also be a negative association. So there are many examples where it would be useful for us to allow for a sampling distribution that can handle both positive or negative associations between the components of the counts. So using this this structure of the Poisson model is not going to allow us to do that. Therefore, I think this paper, the JSPI paper, showed that if you can bring in a mixture of count distributions of the type that we saw earlier, you can in fact have a model that allows for both types of associations and also allows for over dispersion. So that if someone was trying to use this kind of framework, if you have made up your mind to model using a multivariate distribution, then perhaps the H mixture, a finite mixture of these multivariate Poisson distributions could be useful. Now, having decided that we want to do this, clearly, if I want to go through a Bayesian framework, I should be able to write down and evaluate the likelihood easily. Then I have to put some priors on my parameters, right? And then do posterior calculations. Now, we have to therefore evaluate this multivariate PMF fast, because we want this whole thing to be scalable and computationally efficient if possible. And we also then have to evaluate this mixture PMF. So those of you that are have done a lot of Bayesian calculations can possibly almost anticipate how we will handle the mixture. So here we go. So suppose this is the finite mixture distribution. Is everyone comfortable with that? MPM is the single Poisson, M-variate Poisson that I write using the Carlis-Melixidau's 2005 structure. Then with some mixing proportions, pi's, I am willing to write the sampling distribution of this M-variate count vector in this form. Which means what? Each one of these lambda h, this will be a lambda h now, right? So my set of parameters will be lambda 1 through lambda h, these vectors. And then we will have pi 1 through pi h minus 1. One of them, if they sum to 1, right? And let sigma h be the diagonal with each one of these lambdas on the diagonal. So this will be the mean and covariance structure of such a H mixture. Let's put that into our observation equation. So this is going to be the conditional distribution of YIT. This is still a vector. What do I want to do? I want to take a log of this lambda ITH. Remember, lambda is a vector. This is a vector lambda. So I'm going to model for each of those Q, I will set up a log linear model. Now the predictors are what the science tells us. So I can have exogenous predictors that are location time varying. I can have, yes. So here in this particular case, what we did was we said that let B be J sub I sub T. So it's exogenous predictors, but then the coefficients, the deltas that I put for that are location time varying coefficients. Then I have another set of coefficients that we put in. where the coefficients eta jh, they do not vary by location or by time. So it's you can do whatever you want, right? This part is up to the particular example that we are working with. But in general, we will have this sampling distribution in the observation equation. And then, of course, we will have a log linear model, a suitable log linear model for the underlying lambdas. This is just the construct, and I'm saying let beta IT be a PD dimensional vector. So after you've written out your second equation, collect all of them into one vector. Let's call that beta sub IT. In general, it's going to be location and time varying. So the structural equation will relate the location time varying parameter to this gamma T, as I said before, a pooled parameter. So we can do something like this. I just put an example here. The important thing is that at this point, this VIT is a multivariate normal random vector. Then we have the state evolution happening only at the gamma T stage. This is like our usual Markovian evolution. So we now have an observation equation, a structural equation, and a state equation. We can write down the likelihood function. You see the likelihood function. Right now, I just wrote this as a single normal, but you can put that as a mixture normal if you want. For simplicity, I just wrote it out here, but then you can write this as a mixture normal. And remember I said you can use the Diebold-Roberts idea for sampling under a mixture normal. Those details are in the DVTS handbook paper. And if people are interested, I'm very happy to talk more about those things and how we did the implementation. Then you put some prior specifications. Here we put some very, very routine prior specifications, and then we can carry out the posterior distribution, write out the posterior. And here I've just written this small note about the Diebold-Robert. In the interest of time, I'm going to skip this and keep going. But again, if people want, we can talk more about this. Then we apply the Gibbs sampler, right? And then in this particular case, I don't know if people are aware of time series specific things, but we employed this forward filtering, backward sampling procedure in order to generate the gamma T. Once again, I do not have the details of that here, but I'm very happy to talk to people about that if you're interested. Inverse Fisher draws for the covariant structures and Dirichlet draws for the proportions. And then, you know, we can do all of this pretty seamlessly. And there is nothing really new happening here. This is just the usual machinery that we employed. And then we are able to get our estimates. We have all the details in that SII paper. And then we can also, like I said, we can fit univariate models. This is one species of snails. This is another species of snails. You can fit individual models to those species, and then you can get the in sample mean absolute deviation and the out of sample or prediction mean absolute deviation. So prediction mean absolute deviation means we have to hold out a portion of our data and then, you know, fit on the training part, predict the held out part, and then calculate the mean absolute deviations of the predictions. So we are able to do that all in the Bayesian framework. And then we have a bivariate where we employed this result is based from not the H mixture. This is just based on a straightforward bivariate Poisson model. So we can do these kinds of model selection. And here are some pictures. We just chose 2 sites to show these pictures. You have sites 14 and site 22. We had a lot of locations on the grid, about 40 locations on the grid, and these are from 2 of those locations. So now you can compare the observed to the fits. Yeah, the usual data analysis that we would do. Any of these things can be done. Okay, so in this case, we are particularly plotting the gammas. We just wanted to see how the gammas evolved. And like I said, there is a lot more in that paper. There were hurricanes at 2 points in time. So we can take a look at these gammas, for example, and see if they changed as a result of the hurricane and so on. Okay. Okay, so here are some of the results. There's not much. These are just illustrations. 2 things here, and there might be something here for students if they are interested. One is the speed at which you evaluate the multivariate Poisson PMF. Direct evaluating, I'm not talking about the H mixture. I'm only talking about the multivariate Poisson PMF itself. It's a pretty slow calculation. There was one recurrent scheme that was proposed here. And then one of my students, Shan Hu, in her thesis, she modified this and proposed a slightly faster approach. And we did some time calculations. We did not spend too much time on this. We did some time calculations. And although we felt that our method speeded up the likelihood calculation somewhat, it was not fast enough, especially once the N or T starts becoming large. So certainly if there is a nice way to speed up the multivariate Poisson calculation, that would be extremely useful for this type of modeling. So we went another direction and we said, okay, because of the slow speed of doing the multivariate the multivariate Poisson calculations, are we able to do this level correlated model? So we basically, as I said before, each component will conditionally have a univariate distribution. One of the nice features is that we can allow different component univariate distributions. Like one component can be Poisson, one can be negative binomial, one can be zero inflated Poissons, that kind of stuff. We can build a dependence through the latent Gaussian process. And we use the R-INLA approach to carry out approximate Bayesian inference. And here are a few references that relate to this. I would also like to mention, if for people that are interested, a book that should be published in 2022 by myself, Balaji Raman, who is a collaborator in India, and Rafik Sawyer, who is a strong Bayesian. He's at George Washington University. We have this book on dynamic time series models using R-INLA. The main goal is, when we started working with R-INLA, when my students started doing this, we had a steep learning curve. We had to spend a lot of time to understand the syntax and then to modify it and then to expand it and so on. So that was why we wrote this book, hoping that if other people are interested in R-INLA and interested in doing time series dynamic models using R-INLA, maybe the code and the notes that we have provided could become useful. So this should be coming out very soon. So the data structure is the same as before. Yes, so I just basically wrote out what I had before. Let's write out the LCM. And just for variety, I am showing you not the ecology data, but another data where this is ride sourcing, right? We're all used to using either taxi cabs or Uber or whatever is the version of Uber in our own countries, right? So we are looking at daily data on the number of TNC. TNC means these these kinds of ride sourcing things like Uber or Lyft versus taxi usage over 3 years from 34 taxi zones in Manhattan. So we just wanted to look at these kinds of data. So 34 will be the number of time series. And then of course, it's going to be a bivariate time series because I'm looking at Uber, I'm looking at TNC and taxi, and then we are going to put some predictors. So we have training and holdout data sets, and we have discussed this data in our book. So here is what a level correlated model is going to look at. Remember, J goes from 1 to M. M is the number of component time series. So I'm going to say that each univariate component conditionally has some UDC, means univariate distribution of counts, with some with the mean lambda JIT. And then I'm going to take this lambda JIT, take the log of it, and I'm going to fit whatever is a sensible log linear model to this thing, depending on what I have, right? So I just put something like this. Here is a level, here is some kind of a time trend, which is gamma. There is like a linear time trend. And then there is this time varying, location varying intercept. And then ZTs can be a bunch of predictors that you put into the model. I've just said 3 here because I'm going to tell you what the 3 are. And then there are coefficients beta L corresponding to them. I'm making them static. And then there is this level correlated error, which I will explain in a minute. Then you take this time location varying beta, and you can model that as a random walk, let us say, or I can model that as an AR1 or an AR2, some kind of a temporal evolution that I put for this model. And we are going to use this INLA approach. The INLA approach, if people are not familiar with it, was introduced in a sequence of papers by Harvard, Rue, and collaborators. For example, there is this JSPI paper, there is the ARSSB paper, which are very nice to read. And then, of course, there is this R-INLA website. It is not part of CRAN. It is its own standalone website. And we can invoke this. Here is a brief review of INLA. Suppose I have this data vector and the vector of latent Gaussian variables. Let's say the dimension is n, same as the data, and theta is a vector of hyperparameters, usually small dimension. Now we assume that this xn is defined by a Gaussian Markov random field, which is explained in this Rue paper. This can be expressed in general as a 3-level hierarchy. We have yn given xn theta follows some data model. Xn given theta follows a Gaussian model with mean 0 and covariance sigma. And the theta is a vector of hyperparameters, which we model as pi of theta. Okay. Now, let this xn minus lm denote all the other elements of xn without elements L and M, say. Now, INLA describes these posterior marginals that are of interest to us. First of all, we want to get the posterior inference on the xi's, which are like the betas that I talked about earlier. Xi's given the data, which can be expressed as the integral. You're going to integrate out with respect to theta, this product. Likewise, we can get the posterior of theta j given the data, which can clearly be written like this. Okay, this is theta j, and theta minus j is all the other thetas. So INLA is now going to construct approximations to these guys. So suppose I just call an approximation to that as pi tilde, and an approximation to this as pi tilde here. And all I have done between here and here is to put tildes over all the components that I have here. So anytime I see a tilde, it is going to be the approximated density. Usually INLA consists of 3 steps. First step is to approximate the posterior marginals of the hyperparameters. So pi of theta given yn, we are going to approximate that using a Laplace approximation. Okay, how do we do that? We do that by approximating this pi of xn given theta yn using a multivariate Gaussian density denoted by pi tilde g. Then you use the well-known Laplace approximation. Okay. Step 2 is to get the pi of xi given theta yn. Okay, so you want an approximation for the latent Gaussian variables given the selected hyperparameter values and the data. They use one of these three, Gaussian, simplified Laplace, or Laplace. Of course, the Laplace is preferred, but if you want a faster run, you can use the simplified versions. The third is to use a numerical integration step to finally get the conditional approximation of xi given all the data. So these are the three steps. I mean, these are Bayesian steps. I'm not going to be focusing on this. Let me instead say how we can do time series with this kind of stuff. So INLA provides us with approximations to these things. We need one step ahead forecast distributions in time series. So we need things like the probability distribution of yn plus 1 given all the data up to what we observe. And clearly we can write this distribution, correct, as the probability of yn plus 1 given the unknown latent xn plus 1 theta yn times the posterior of xn plus 1 theta given yn, integrating out the xn plus 1 and theta. Okay, which then will become, because the yt's are conditionally independent given the xt's and the thetas, we can write this using as the next step here, right? Yn plus 1 given xn plus 1 theta, because then it doesn't depend upon the y's. So this step is straightforward. And then we just use whatever approximations INLA had given us earlier, we can plug in here. All I'm doing here is to say that we can easily use the INLA machinery to do estimation as well as prediction. That's all. So we include zone-specific fixed levels, a linear trend gamma t, fixed effects, etc. These are the predictors, like I said. We can include a dynamic intercept, which we model as a random walk. We can also include that level correlated effect, which brings in the dependence between the TNC and the taxi component. So this becomes a bivariate. Sigma will be a 2x2 covariance matrix. We should estimate that also. So I'm writing out the same model here. UDC we assume to be Poisson. You could assume something else. We set up the formula by assuming that these levels are fixed. We use R-INLA for fitting the model. The code would look something like this. So we have to set up a formula, just like we set up LM, etc. in R. We set up a formula for this in INLA, and then we have to estimate this by calling this INLA function with this formula, and then we kind of say what family we want and so on, and this will give us the posterior summaries. The posterior summaries would look something like this, right? So looks very much like our output. And then we can use inla.posterior.sample. So it allows us to actually generate samples from the posterior distributions that we have, and then we can make plots, right? You can plot the observed and the fitted counts. So in this case, we have the TNC observed and fitted and the taxi observed and fitted, and you can kind of see that as the TNC is increasing, the taxi is slowly decreasing. So you start making all kinds of posterior observations. Then we fit other models. We fit a second model. I mean, you can do whatever you want. You can basically adapt whatever models you want to fit by changing this line to whatever you want. So once again, I can fit this model and I can get counts, etc. from that model. And like I showed you before, we can make model comparisons. We can compare using the deviance information criterion, the Watanabe AIC, and then the average mean absolute error. We can compare the models and then choose the model that performs better. All right. So basically, this line is just supposed to say that INLA allows for certain other distributions than Poisson or than the Poisson. For example, INLA allows you to give a negative binomial or a zero inflated Poisson structure. The code is slightly different. It's in our book, or we can share it with anybody who is interested. Let me end this talk by just mentioning some extensions and other approaches. Now, what if I want to use a sampling distribution in the LCM framework and R-INLA that is not allowed by R-INLA in its canned functions? For example, when Marino and Katiani were visiting me, we wrote papers that talked about two extensions of count distributions, right? And so what if we wanted to use one of these? My thought is that there is a function called R generic in INLA, which allows us to write our own likelihood and stuff. So maybe we can leverage using some of those distributions through the R generic function. We have not explored this, so maybe this is something that one can explore. I also want to point out that the LCM is not the only way for handling dependence. I know that many people like to use copulas. I personally have never used copulas, but you can always use copulas to model the dependence. There is one paper in Communications and Statistics, and there is a recent non-parametric copula paper that I read. So anyway, this can be done. There is also the simultaneous graphical dynamic linear models that can be used as an alternative. Yet another alternative, not in the Bayesian framework, but in the observation-driven in our class, that can also be done. And maybe we can extend that to the multivariate framework. So these are extensions of, there are many, many nice things to be done in the multivariate count field, I think. Thank you very much.
Thank you, Nalini, for the nice talk. We have time for some questions. Any questions?
Mario, may I ask a question?
Yes, Michel, please.
Nalini, thank you for your great presentation. It was very interesting. It's actually a topic of interest to me. So I really liked your presentation.
Thank you.
Usually people work with Bayesian things using MCMC. It's the more conventional way to derive the posterior estimate, right?
I'm sorry, I missed that crucial part. Using what?
I'm sorry. Usually people do Bayesian things using MCMC.
Yeah.
And it's different from INLA. INLA is, okay, I heard something, I'm not an expert on it, but I saw you in a presentation, you draw some posterior samples, which I believe it's different from the posterior samples draw from MCMC, right? And it's just to be sure. In your posterior sample that you showed by the Uber data and taxi data, we see some inclination, some trend, but this is not because this is actually a sample time by time, right?
You're talking about this, correct? One of these, right?
Exactly. No.
Yes, the x-axis is time. Yes.
I see. It's because
I'm only plotting the posterior means here.
Point wise.
Time wise, posterior means, yes.
Time wise, exactly.
Yeah.
Yes, because usually when since we are not so used to INLA, when you see this, we think the first thing to think is that the chain has not converged.
It is not a trace plot, no.
Yes,
but what one can do in INLA, and we have discussed that, and I'm very happy to discuss it with you, because I think the more comments people write, we can develop this in INLA better. at each time point, it is possible to draw samples so that I can do trace plots at each time point, and I can actually do the posterior distribution at each time point
without worrying about convergence, because you do not, I suppose you do not have to worry about convergence, right? As you do in MCMC samples.
You do not, and that I think is the advantage here.
Yes.
Right? So the whole idea is, see, we struggled, as I showed. That's why I wanted to show you the first part where we had done MCMC, our very conventional way of gap sampling for doing this problem, right? But when we were working with, think about having 6,000, IN is 6,000. We were working with a marketing problem where the I goes from 1 to 6,000 something. And then the T is whatever, right? So when you really have a large data set, we just could not have this. It ran for days and days and days and nothing would happen. So that is when my student and I started looking for an approximate Bayesian stuff. We all know you can do variational inference, right? I mean, we can do VB. But then we came across this INLA, and my student explored this. And I think it is really fast. I mean, it is the difference, Michelle, between many, many days and not seeing any output from your data. And within a few minutes, maybe 15, 20 minutes, you can run this whole thing and you see this. But to your point, my student who was working on this first ran on some simulated time series, on some simulated data. The student ran MCMC, ran this INLA, and we made sure in our problems that the results matched. And I think Howard Drew and his collaborators, my understanding is that in many cases, they have done this to make sure that we are not in some transient space, right? We get some answer. No, we tried simulations and made sure our results matched.
I see. And since you touched in this point, I will ask you about the time of process. It's much faster, right? As you just said, about minutes compared to days in MCMC.
Exactly. It's very, very fast.
Interesting. Thank you, Nalini.
Any more questions? Nalini, I have a question. I think it's a general question. Is there any way to assess the fit of the model? How to assess goodness of fit?
We use DIC. Oh, you mean you want to, well, the three criteria we used were DIC and WAIC, mainly for comparisons. We also looked at the in-sample mean absolute deviations because I have my observed counts and I have my posterior means. So I tried to see whether they were close. I also did that for out of sample. So let's say I had, I kept aside some time portion. I used the fitted model and I got my posterior predictive distribution of the future. And I compared that mean with the observed mean that I held out and found the MAE. Those were the things we did. But I mean, if you have other suggestions, we can certainly see whether we can pull out the information, let's say from INLA, right? That's the point now. Because if we were doing our own coding and MCMC, we can do whatever we want, right? We have the entire set of samples. Here, I think we can do, and we need to see. What goodness of fit are you thinking of, Mario?
Some kind of residual QQ plots, this kind of machinery.
It's counts here, so.
Right.
Yeah, we have not thought about. Yeah, we have not thought about residual plots themselves. I suppose one can always get the residuals at that latent state. We've never thought about plots in that sense. Yeah.
Okay.
The DIC in some sense is a summary of my deviance residuals.
Right.
So, but we haven't thought about actually pulling the residuals out and looking at residual diagnostics. We haven't done that, but I'm sure it can be done.
Right.
Right.
Okay, Nalini. Thank you again for the presentation.
Thank you, and I welcome questions or emails, even if people think about something later. Thank you for inviting me.
Okay. You can stop sharing your screen.
Yes. Okay.
Andressa?
All right. Thank you. Can I leave now?
Yes, you can.
Okay.
Thank you, Nalini. Bye. See you soon.
Bye-bye. Thank you.
So Arita is already here, so let me just allow him to, let me see. I think he's already a co-host. Oh, no. Just a second. Ok. Silvio, pode liberar o Arita para ser co-host? Just a second. We are allowed you to present. So Magno, if you can just turn off your video, everybody can see you now. Magno. Silvio, você conseguiu colocar o Arita de co-host? Eu não consigo.
Just a moment, Arita.
Just a second. Oh, okay, there you go. I think now you can try. I'm sorry about that.
Oh no, this is a crazy time. We're all getting used to Zoom, and yeah, I totally get it. Let me try and share my screen. Okay. All right, so can you see my screen?
Yes.
Okay, all right, that's great.
Yeah, but it's not full screen. I don't know if you...
Sure, I can do that full screen. Is better?
Yes.
Yeah.
So you want me to start right away?
Just a moment. Let's start, Andressa.
Yeah, you can introduce Arita, I think.
Yeah. Okay, Arita, thank you very much for accepting our invitation. It's a pleasure. Let me say a few words about Arita. Arita is research assistant professor at the University of Virginia, USA. And research interests includes spatial and spatial temporal modeling, optimization. He likes to work with various data sources and statistical modeling. And Arita got his PhD from University of Connecticut, USA. Please, Arita.
Thank you, Mario, for the nice introduction. So the title of my talk today is Bayesian warming for spatial and spatio-temporal Gaussian processes. So this is a joint work with Dr. Sudipta Banerjee, Dr. Deepak Kade, who is my thesis advisor, and myself. So thank you again for inviting me to give a talk, and I really look forward to this talk for a long time. And thank you, Andressa, and the entire organizing committee. So without further ado, I'd like to get started. I will be focusing primarily on the spatial part of it. As you can see that, as you'll get to see that if you understand the spatial part of it, then we can essentially extend it easily to the spatio-temporal version of this. So I'll just give some background first to start off with. Data with spatial information essentially manifests in a variety of domains, including environmental, geographical systems, etc. Then you have a lot of applications in digital cartography and terrain modeling, biomedical imaging, spatial econometrics and land use, which has seen a lot of use of spatial modeling over the years. Then there is this application to evidence-based public policy, and as well as what we have all seen for the last 2 years or so, a huge application to epidemiology and public health, with all of the spatial research going on with the spread of the coronavirus. And so the main focus of my talk here is to understand how to bound regions of change within a given spatial reference domain. So not all regions of the spatial domain with respect to a given response process exhibit homogeneous change. In some areas, you see very rapid change. In others, you don't see a lot of change. By me saying change, I mean a lot of spatial correlation within that region, jointly showing a spike in a spatial plot that you will see. So I'll try and introduce it through plots and images to make it easier to understand. At first, what we want to make clear, just before we get into the details, is that there are many scales for analyzing spatial data. As all of you know, and anybody familiar with spatial data is used to, there is this aerial referencing where your units, your spatial units, are essentially zip codes or counties, or there is this point reference data where you have latitudes and longitudes, and you essentially have a continuous spatial indexing by the use of a choice of distance measure. You could use an Euclidean distance, and there are multiple other distances you can use to apply the same methodology to other manifolds. So in this work, we assume that the region of study lies within the D-dimensional Euclidean plane. In particular, for most applications, D would be restricted to 2. So you have the Euclidean plane, and Y indexed by S is essentially our spatial process that we're interested in inferring on. And of course, this process is observed at a finite set of locations, using which we essentially infer on the entirety of the surface, which is, of course, continuous throughout the domain. So the continuous indexing allows us to extrapolate through various known methods of kriging and similar statistical literature. Excuse me. Did anybody have a question?
You can keep going.
Oh, all right. So I thought somebody had a question. Okay. So so an inferential framework for this spatial process is then developed by inferring on the surface that is produced by these finite sets of locations. And then we analyze its topological characteristics based on looking at the surface and developing mathematical tools that allow us to quantify such change. So by me saying topological characteristics, I mean boundaries, peaks, troughs, etc. So all of this is done based on observed data. Now, the topological analysis of the interpolated surface naturally starts with considerations of smoothness of the surface. How smooth is the surface that you're looking at? So observations over a finite set that I just mentioned are not indicative of this process smoothness, since the finite observations provide some level of discreteness, which does not bode well when we're trying to understand smoothness of a process which relies heavily on the continuous spatial indexing and the continuity of the surface. Right. So inferring on smoothness, therefore, naturally transfers into the process specification. How do you specify these processes to start with? And we try and create and develop methodology that essentially relies on the specification rather than the finite observations to to infer on the process smoothness and therefore develop framework which is then used to quantify these topological properties. So in terms of background or research that has already been established, these changes are essentially quantified through gradients. As you can understand, since you have a continuously spatially indexed region, there exist gradients. If the spatial region is smooth enough to admit gradients, then change within this spatial region is quantified through these directional derivative processes. Why the direction is important? It is because we want to find out the direction of the maximum change. We don't want to, because change is happening. If you think of a point within a spatial reference domain, change could happen in any of the 360 degrees that are available to you. But we're only interested in that 1 degree where you see the maximum amount of change. So the choice of direction here is really important. And the development of this directional gradient process continued when coupled with this continuously indexed spatial process, of course, prompted interest in the differential behavior and inference for lower dimensional structures within the surface, like how do gradients behave on curves, right? And of course, the smoothness of these process realizations generally depends upon the process specification, as I talked about. So the process specification, of course, by that I mean the covariance function that you choose to essentially specify how is the response at location S related to the location S dash, right? So if the covariance matrix that you use to generate these spatial processes through a Gaussian process is smooth enough or is differentiable up to a certain order, then that guarantees the smoothness of your produced process observations that the finite realizations are just a snapshot of. Right? So by lower dimensional structures, when you look at inference for these lower dimensional structures, by lower dimensional structures within the spatial surface, what I mean is curves, right? So you want to bound regions with these curves of interest that essentially bound maximum change within the surface, right? So if you see a peak, you want to bound that peak and say, this is the place inside the spatial reference domain where most of the change is happening. So these curves were essentially termed as difference boundaries or Wombling boundaries, named after the seminal paper by Womble in 1951. And then Hanergy and Helfand essentially extended this to a Bayesian framework where they considered Bayesian inference for these difference curves, right, when embedded within a spatial surface. Now, sharp gradients, of course, are indicative of maximum change, and sharp gradients along these curves are indicative of maximum change bounded by these curves, right? So this work that we essentially start off with talks about the second order change, right? So how much is the curvature? So just inferring on gradients allows you to understand where the change is happening, but how sharp is the change? Gradients are not informative of, right? So to understand that, you need by just simple high school math, you would understand that when you're looking at how fast a curve is increasing, the first thing is to see if the curve is increasing or not. So that is addressed by gradients, but how fast is it increasing is addressed by the second order gradient, right? So the same kind of thing, the same kind of simple concept is applied to these surfaces, right? So then with the given choice of direction where the maximum change is happening, we are now interested in how fast is the change occurring. Throughout the curve, is the rate of change homogeneous or not? Right? So that gives you an understanding regarding what is the shape of the peak or the shape of the trough that is being formed by these spatial processes, right? So once this framework has been put in place, we would also like to incorporate this framework into the Bayesian wombling. So this is more commonly termed as curvilinear wombling, where your gradients and your second order gradients are then inserted within the curve to kind of see along the curve where the change is happening. Where is the maximum rate of change and how fast is that change happening throughout the curve as you traverse the curve. So the treatment of curvature, of course, is very central to differential geometry. If you open any standard book, any standard one of these references, you would find a whole chapter dedicated to just studying curvature of surfaces in R3, right? So we ground the framework, the theoretical framework of this entire development that is housed within this paper inside of differential geometry. But we will not get into those details and just see how the inference translates when you use these concepts within a spatial hierarchical modeling framework, right? So in terms of making things clearer by use of images. I think I have 3 images in the next upcoming slides. This is the first one of it, which essentially makes it clear to you as to what I'm talking about in these last 2 slides. So you see C is the curve marked in blue. The surface S is just shown, like a snapshot of the surface is shown. Since we are talking about surfaces in R3, you have your S1 and S2, that is your Euclidean plane, and you have your height function Y, which essentially is the surface. So within any spatial modeling you do, you understand and infer on the surface by looking at plots like this when projected on 2D, right? So you project this surface on 2D, make a contour plot of some sort, and look at areas which have maximum change, areas which don't have change, and then you try and show that plot to kind of address the fact that how much of this, like how much of spatial heterogeneity exists within your application, right? So we are talking about analyzing the surface itself, right? So as you see, the curve bounds the peak, of course, and then at a specific location that is marked, you have 2 normals, one that is a normal to the surface and the other one that is a normal to the curve. So the big NS here denotes the normal to the surface, and the small ns denotes the principal normal to the curve. Now there exists an angle between the normal to the curve and the normal to the surface. Of course, as you traverse this curve, the direction and the angle of the normal, the angle in between the 2 normals would change. Now this angle essentially quantifies curvature, which essentially talks about how fast is the response increasing, or how fast is the change in the surface when you go from one point to the next. And the shaded region is essentially the local tangent plane at which you are looking at these angles, right? Now, what does wombling in to do is that project this curve onto this 2-dimensional plane, and then that is what you like essentially end up seeing. So when you project the curve, then you have a projection of the peak and a projection of the curve as well. So you want, so that is when you would get to see where your direction becomes very important. So the direction perpendicular to the curve is where maximum change is happening, right? Because that is exactly where, if you can see from the picture, the peak is housed. So you want to quantify and capture that change. Of course, when you traverse the curve, as you can see by looking at just the surface, that the rate of change is not uniform across all locations of the curve. And that is what is addressed by curvature, and that is what we want to develop a framework to capture within a Bayesian hierarchical setup. Now, what does wombling essentially do? Curvilinear wombling essentially do is that it picks up this curve from the surface, and then considers an approximation of the curve. So by me saying approximation, I mean rectilinear approximation. So if you choose a certain partition of the curve, a fine enough partition of the curve that guarantees that you capture the intensity of the peak that is enclosed by this curve with sufficient accuracy, then what you end up doing is then joining subsequent segments with the subsequent points of your partition with a small line segment, and looking at the direction perpendicular to that segment to see how much change is happening across that line segment. Now, if your partition is fine enough, of course, by standard theorems in calculus, you can understand that you would be able to capture change throughout this curve in a very accurate fashion. Right. So now I'll just briefly go over some theory. I will not get into much detail so that, like with the interest of time. So what we end up doing is we quantify these gradient processes using your standard Taylor expansion. So the first order term talks about the gradient. Of course, all of this is spatially indexed with respect to a continuously indexed spatial process. And your second order, that is your Hessian, which is also a spatial process now, is produced by the second order expansion. And naturally, you have these remainder terms which go off to 0 at a certain choice of a spatial scale, right, which is given by h. So these are your standard definitions of gradients. Of course, we assume these exist when your process is continuous, and by me saying continuous, I mean mean square continuity, which is defined as this. If you have a sequence within your spatial reference domain which approaches or converges to a certain point, your response process will also converge to the response at that certain point, right? So that is the sequential definition of continuity that I use here, which is easier to interpret in some sense. So of course, using those equations, you can then get your finite difference gradient processes. What you can see here is that these are all linear combinations of your original process, just lagged by a scale h. So this goes a long way when we have this Gaussian assumption on this, because since these are linear combinations, they also, these gradient processes, as you can see, when constructed in this finite difference manner at a specific scale h, can be inferred to be Gaussian. And then when you pass on to limits, you allow h to tend to 0, where you actually obtain the gradient. These limits, when shown to exist, establish the validity of these processes. So that's the first part that we do. So what we form here essentially is that a process y, when observed over a certain d-dimensional plane, induces a gradient process and a Hessian process, right? So their validity is guaranteed as long as all entries of this joint covariance matrix exist, right? So as you can see, this involves fourth order derivatives of the covariance function that was used to specify the process originally, right? So for your full Hessian to exist, you need your covariance function to be fourth order differentiable. For just the gradient to exist, just second order differentiability of the covariance matrix that is used to specify these processes is just enough, right? Then of course, these processes come from a spectral function which ensures the validity of this covariance matrix. You do an inverse Fourier transform of this spectral function to guarantee that the covariance matrix exists. So the same kind of theorems that we looked at for which required fourth order differentiability of our covariance matrices could be extended to see that the generating function within the spectral measure also has a finite fourth moment. So we look at some examples here, which are linked with commonly known covariance functions. And yes, so the only covariance functions that are amenable to such full-scale gradient analysis are the Matern kernel, which is very heavily used, and the squared exponential kernel. In particular, we look at the Matern kernel with the fractal parameter that guarantees smoothness of order 5/2, right? And that produces smooth enough observations that we can use. If we look at the fractal parameter 3/2, only the gradient process exists. The Hessian does not exist. All right. So in terms of Bayesian wobbling, what we aim to do is that we aim to look at some wobbling measure along the curve, and we want to do a line integral around the curve to quantify the amount of change. And of course, every single time we want to look at the direction that is perpendicular or the principal normal to the curve, right? Because that's where maximum amount of change is happening. So I'll not get into too much detail in terms of how how we obtain distribution theory for these measures, but then we go back to the linear combination of the difference processes that were formed to then address the fact that these wobbling measures, being functions of those difference processes, are also Gaussian when we have this Gaussian assumption, right? So this just shows you that this just goes to talk about what I just said in terms of our Gaussian assumption, right? As soon as we have a Gaussian assumption, jointly you can show that the wobbling measure, being a function of the difference processes for the gradient and the curvature, are also jointly Gaussian, that is shown here with some mean and some covariance, right? So we all inspect all of this within a Bayesian hierarchical framework for doing spatial modeling. As you can see, your mu SB is essentially your X transpose beta, which is a general linear model that you put inside, and ZS is your spatial effect that you hope to infer on. So this functions on the residual surface. So you perform wobbling on the residual surface that is given by ZS, right? And your epsilon S is essentially a nugget. So you fit the model and then you look at the surface that is produced and you analyze the surface in simple terms. And of course, we assume that ZS is a Gaussian process with an appropriately chosen kernel, which will be, of course, dictated by the application that you choose. So the kernels that I just showed you, you choose in between those kernels to see if you want to have inference for the gradient process or if you want to have inference for the gradient as well as the Hessian. So sampling, posterior sampling goes on with through the use of compositional sampling. So you want to infer on the gradient and the curvature process on this residual surface given your data, right? Because you let the data speak for itself in terms of how sharp the change is, how sharp the gradients are within your residual surface, or how sharp is the rate of change that is given by the Hessian within your surface. And once you've done that, you can, of course, choose the curves where you want to perform Womling for, and then go about doing that through your Womling measures that are formulated for that particular curve over this residual surface, right? And for our application, this is the customary prior assumptions that we have, which is very standard. And all of you have, if anybody is used to spatial modeling, they're of course used to looking at structures like this. I will not get into too much detail. You just have a normal prior on your regression coefficients, a normal prior on your spatial effect, and an inverse gamma on the nugget processes variance, and inverse gamma on the process variance for the spatial effect, and for the spatial scale, we have a uniform parameter. We have a uniform prior specified. So we did some synthetic experiments. In terms of synthetic experiments, we wanted to check if these gradients are recoverable. These gradients and curvature are recoverable for data that is not from the model. So as you see, we generate observations from a pattern that the model does not know. The reason why we have two patterns is that the first one has no interaction between the two coordinates. The second one has an interaction. So if you take, in simple terms, if you take a gradient with respect to S1, you would not get S2 terms of S2 inside of the first pattern. But if you take a gradient of S with respect to S1, then you would get terms of S2 in the second pattern. Right? So we want to check for these two scenarios, how well the gradients are captured. So as you can see, this shows you, the first row shows you the true gradients, and after fitting our hierarchical Bayesian model with just an intercept, this shows you your estimated gradients. And this is your curvature for the first pattern. Of course, as you see, that there's no interaction between S1 and S2, so there is, the mixed gradients don't exist. And this is what our estimated gradients are. Estimated curvature is, that is the second order. The main reason why you see 3 is that if your Hessian in 2x2 has just 4 entries, but then the cross term is like 1, 2 is, so H1, 2 is similar to H2, 1. So you just look at 3 unique terms and plot the surface for that. We have to always remember that the Hessian is a spatial process, right? So that's the reason why you have this continuous indexing, and you can capture this. Then we went to perform Womling. So we chose these level curves that you can see, which bound peaks and troughs and valleys and stuff like that. And we wanted to see if the true gradients, so the main reason why we choose such an application is that these patterns that you can see, your gradients and your curvature and your Hessian is available in closed form, right? So you can actually compute these and compare them. In reality, these don't exist, these are not observed, right? So that is the reason why within a synthetic experiment, it is very important to document if the true value falls within the credible interval or the highest posterior density interval of these estimates that we are, this inferential framework that we are proposing, right? So as you can see, the curves that we chose, we could compute the true average gradient, the true average curvature, and all of these fall within the HPDs that were produced. And the one place where we chose this curve D, where you see there's not much change happening, so you would expect things to be not significant. So what happens here is that if your highest posterior density interval does not contain 0, then you say that it's significant either in one direction or the other. So the gradient is increasing or decreasing. Similarly, the curvature, the normal lies above or below the surface, right? So the concept of concavity and convexity, right? So if you have 0 within the interval, then there's no significant gradients or no significant curvature, right? So that was very well captured. As you can see in curve D, most of the curve lies in places of no change. So you would not expect to see high rates of change there. So no curvature should exist, and that's exactly what we see. This is the only HPD interval that contains 0. Right? We then applied it to some standard classical data sets to see how much of this is actually would actually make sense. So the first one that we choose is the Boston housing data, which has been analyzed in multiple papers, and it's very indicative of the differential house price behavior when you look at a big city like Boston. So what is apparently immediately visible here are these two zones where you see very high median house prices as opposed to very low median house prices. Now we're aware that these house prices are medians when aggregated over these census tracts, but we translate this to a point reference level by looking at the median of the census tracts. right? And then just looking at the median house price as a spatially indexed process with respect to locations that are medians of that are centroids of these census tracts over which we observe this housing behavior. So we fit the model. As you can see, this is the posterior estimate of the model and the process parameters. We have a small spatial scale due to these large zones, large contiguous zones of similar behavior. So that's the reason why your spatial scale is small. A large spatial scale just indicates that the spatial correlation falls off very fast, right? And you have your process variance given by sigma squared, and that's much larger than the nugget variance, which is essentially microscopic variance. So that just indicates that most of the variation within the surface is being dictated by your spatial effect. And we just fit the model with an intercept. So this is your, so of course it ended up being significant as we didn't include other covariates as well. Then we go on to this, we go on to constructing these boundaries where we want to do wobbling. So as I said, there are these two big zones of similar house price behavior. We wanted to see how much of them actually have significant gradients and how much of them have significant curvature. So as you can see, the curves are being constructed with the spatial process being fitted in your leftmost plot. The center plot essentially shows you how much of the gradient was significant with bold lines indicating significance. And I'm not sure if you can see here, but then if you zoom in a bit, you can see that the colors actually change. So so the area with red essentially has a positive gradient, and the area with blue essentially has a negative gradient, which denotes a valley, and the area with red essentially denotes a peak, right? So then we go on to the second order. How fast is the response increasing, or the rate of change in the response, the rate of change in the gradients, I mean. So you see the maximum and the most rapid change is happening right here when you cross over from very highly priced houses to very low priced houses. So that's exactly where you see this, the curvature turns out to be significant in some sparse areas within this, right? So there is still some residual effect residual spatial effect of nature that exists after you fit your spatial model and just look at the surface, right? So that is being quantified by these inferential frameworks created for performing curvilinear wobbling on these curves, right? So without this framework, all of this is inaccessible. All of this inference is inaccessible. You cannot say anything just except just showing the plot, right? So then we also looked at subsets of the curve. As you can see, curves 1 and 2 are much bigger. So we enter into curves 1 and 2 to construct 3, 4, 5, and 6, on which we do the same thing to see how the effect translates as you move further inside these zones, right? So you see much more of these regions show more rapid changes because peaks end up forming. So you actually end up seeing a lot of significant curvature as compared to your earlier plot, right? So then we perform we showed the estimates for your curvilinear wobbling measures here. So the significant ones are not marked in bold, and the ones that were not significant that contain zeros in their HPDs are marked in bold. As you see, some of like in particular for boundaries 3, 4, 5, and 6, which have more peaks inside of them, show a lot more significant curvatures as opposed to boundaries 1 and 2, right? Which are not, which still have significant gradients, but then less of significant curvature. Right? So then we considered another application where we looked at this Meuse River dataset, which is again very classical. Looks at heavy metal concentrations along the Meuse River. So in this case, what happened in the earlier case was that we had to construct these boundaries across which we wanted to study change, right? But here the boundary is actually available to us, and the boundary is the Meuse River. So we want to see gradients of these heavy metal concentrations across the river, right? So and the river is static throughout these applications. Right? So we did the same kind of we fit the model. Now we have covariates in the model, and we fit it separately for each heavy metal. Of course, this is indicative that this can be extended to a multivariate framework, right? Where you can study wobbling and all of that inside of that, right? So this is what the gradient surface looked like. As you see that each row corresponds to a heavy metal. So the black is your Meuse River, and you see significant gradients appearing for the first heavy metal, which was cadmium, I think. Yes, then copper, then lead, then zinc. So the first two rows are cadmium and copper. As you see, the gradients and the curvature for the heavy metals is very, very different and very heterogeneous, right? So not all regions that show high gradients show high curvature, right? So it's only this northern part of the river which shows a lot of gradients and a lot of curvatures with respect to all heavy metals, but then in these other parts, some heavy metals are more concentrated than the others. And that's exactly what you end up seeing for the next one, which is your lead and zinc. You see lead, not so much. There is not much concentration of lead, but then a lot more concentrations of cadmium, copper, and zinc. And the main reason why this is important is that a lot of these river flood basins are used for farming. They're used for grazing cattle, which is available in that area. So having heavy metals there is essentially indirectly having heavy metals inside of your food, because your cattle is grazing there, you're growing plants there, which you essentially consume. So this analysis essentially shows you that how you can infer on separate heavy metals and their concentrations along this river within a curvilinear Wombling framework, right? So this shows the curvilinear Wombling measures that were computed. And finally, of course, all of this can be easily extended to a spatiotemporal framework, which I won't include and has been extended already. And but then this goes to address the basic concepts that we use within a spatiotemporal framework, where things get complicated when you have multiple correlated surfaces, right? So these curves then change with respect to time, or you can have these curves stay fixed with respect to time, and your response within these curves will change, right? So all of that leads to very interesting inferential theory that can be done. Of course, to produce such a framework, attempts have been made since 1984, but this is the first that we know of where such a framework has been used to address rates of change within a spatial surface that allows us to now classify boundaries or with respect to peaks, troughs, which is not available by just looking at the gradient, right? And all of this has applications just not in this hydrology, ecology, and real estate market analysis, but also in we are looking at applications for biomedical imaging with respect to tumor segmentation by looking at gradients within the gene expression. And so that's where I end my talk, and these are some of my references. Thank you.
Okay, Aditya, thank you very much for the nice presentation. We have time for just one question.
Hi, Mario. I have a question to Arita. Actually, it's more like a curiosity than a question, because in your last slide, if you can go to the next one. Okay. This one, yeah, you said something about epidemiology, and I was thinking about if it's possible to use this method that you present today to us to analyze like coronavirus data. So you are trying to do this kind of study, or? So the main thing is that this is all done within a Gaussian process framework. So if you want to extend it to doing latent wombling, that is when you look at counts. Let's say you're interested in rate of spread, right? So you fit a Poisson hierarchical model, right? That essentially models the rate of change as you go across a spatial domain. Then you can essentially look at the latent effect that you have with respect to the way you do process modeling with respect to spatial effect in these generalized linear modeling frameworks, and then do the same thing on that residual effect, right? Yeah, just change the priors and yeah, exactly. So and just that's nice. But are you trying to do something like this, or you're? So we've been looking at it since you see there are a lot of applications for this. So right now we've been looking at we have been more looking at the imaging side of it, but also we are very interested in looking at epidemiology. But then the problem is that there's so much work that's already been done with coronavirus. Yeah, that's why I know. My slide, right? It's really hard to follow, right? Yeah. Is this
is this something that would be interesting in terms of an application? But then we're definitely interested. So if anybody would want to collaborate, or if you want to do it together, I'm looking forward. Yeah.
That's nice. Thank you.
Mm-hmm.
So I don't know where is Mario. I think he has a problem with the connection.
Okay.
So, okay, so I think I can finish the talk right now. So thank you again, Arita, to accept our invitation. It was really nice to hear your area. Is very different for me, so it was very interesting. So I hope we can see you again, maybe
for sure.
here in Brazil in person.
Yeah.
So thank you.
Thank you so much for inviting me. This has been great. I really hoped that this would be in person. So that's what I talked to Professor Victor about. And that if it was in person, it would have been great. So I look forward to being there in person sometime. All right. Thank you so much.
I hope so. See you then. Bye. So, okay, everyone, let's change the button on your mind and change to Português. Então, agora nós teremos... Agora nós teremos a palestra do Vitor. Deixa... Silvio, você pode liberar o Vitor Amorim? Eu não sei se ele está aqui. Ah, tá aí, já está liberado.
Estou aqui, sim.
Tudo bem, Vitor?
Tudo bem.
Você quer compartilhar?
Deixa eu compartilhar aqui. Eu não estou acostumado com o Zoom. Qual que é o botão aqui?
É o
achei, já
meio
achei.
Share Screen. Acho que está em verde.
Aí está aparecendo, né?
Tá, acho que só coloca em full screen.
Ok.
Perfeito. Então, vamos para a nossa última palestra do dia, uma palestra dentro do grupo de palestras dos alunos do nosso programa. Então, hoje nós teremos a palestra do Vitor Amorim, que é doutorando aqui do nosso programa, sob orientação do professor Sandro Galo e com a coorientação do professor Miguel Abad do IME-USP. Então, hoje o Vitor vai falar para a gente sobre asymptotic Cox Lemma for Heating Times. Com você, Vitor.
Okay, obrigado, Andressa. Como a Andressa já falou aí, eu sou aluno do multidoutorado do IPGES, e esse trabalho que eu vou apresentar, ele é parte da minha tese de doutorado, que foi apresentada ao programa para ser defendida já na semana que vem. Também temos um artigo publicado, que é uma parte desse trabalho, que depois eu vou fazer referência a ele. Então, é um trabalho em conjunto com meu orientador, o Sandro Galo, professor Sandro Galo, e meu co-orientador, o professor Miguel Abad. Eu vou falar de uma versão assintótica de um resultado clássico do que é conhecido como lema de Kark, que geralmente esse resultado é para tempo de retorno, e eu vou falar de tempo de entrada. Fazer uma contextualização para introduzir o tema aqui para quem não conhece, eu peguei um exemplo bem simples de um processo estocástico em tempo discreto, pensar numa sequência de variáveis aleatórias I e D, por exemplo, modelando uma sequência de símbolos de DNA, né, que pode ser modelada também por uma cadeia de Markov e tal. Ou seja, uma sequência tomando símbolos nesse conjunto finito ACGT. E o problema que a gente está interessado é quando a gente fixa uma sequência de palavras de interesse, uma sequência de letras, uma palavra de interesse, a gente vai chamar de palavra, e a gente pergunta qual vai ser o primeiro tempo em que essa sequência vai aparecer na realização do processo. Ou seja, uma variável aleatória. Então, aqui eu coloquei um exemplo aqui de realização, em que o tempo que demora, ou seja, o número de passos do processo que demora para a sequência aparecer, é 35. Uma palavra desse tamanho geralmente tem uma ordem muito maior de tempo de entrada, mas aqui era só para exemplificar aqui. Então, esse é o nosso problema de interesse, essa variável aleatória é o nosso principal interesse. Ela é chamada de tempo de entrada, a palavra A, né? E aí, quando a gente olha para esse problema de tempo de entrada, mesmo no caso I e D, que é o tipo de processo estocástico mais simples, se você fixar uma palavra com N símbolos, a distribuição do tempo de entrada ela não é trivial, mesmo no caso I e D. Eu vou tentar dar um argumento do porquê que não é tão fácil conseguir essa distribuição, antes uma anotação, eu vou usar essa anotação aqui com x subscrito e sobrescrito para denotar essa sequência de variáveis, de n variáveis do processo de k até k mais n menos 1. E aí, quando a gente fala assim, se a gente quer saber a distribuição do tempo de entrada ocorrer no tempo t, a probabilidade de ocorrer no tempo t, tem que acontecer, na verdade, duas coisas. A partir da coordenada t até a coordenada t mais n mais 1, tem que aparecer os n símbolos da palavra, e não pode ter aparecido antes, porque eu estou interessado na primeira vez em que aparece. Então, não pode ter aparecido antes. Isso é o mesmo que dizer que tem que aparecer a partir da coordenada t, mas não pode aparecer a palavra a, essa sequência que eu estou interessado, a partir de nenhuma coordenada anterior. Ou seja, a distribuição do tempo de entrada depende de todas as coordenadas até o tempo t. E mesmo sendo um processo dependente, se você olhar os dois eventos, não aconteceu a palavra a partir da coordenada i, não aconteceu a palavra a partir da coordenada i mais 1, eles não são independentes. Então, o fato do processo ser independente não te ajuda aqui. Tá? Eles não são independentes porque eles têm sobreposição de coordenadas. Então, assim, nosso principal objetivo nesse tema que a gente trabalha é buscar aproximações. No caso aqui, aproximações para o tempo de entrada, e também a gente vai falar um pouquinho sobre aproximações que é o principal aqui, é o objetivo final, aproximações para os momentos do tempo de entrada. Bom, feita essa introdução, fazer agora uma definição mais formal. Então, a gente está considerando um processo estocástico qualquer, tomando valores num conjunto finito ou e a gente considera que esse processo tem uma propriedade chamada que ele é estacionário. O que significa estacionário? É um processo que as sequências I e D têm, por exemplo, né? Se você tomar uma sequência fixa de símbolos, uma palavra, a probabilidade dessa palavra aparecer no processo, ela não depende da coordenada. Ela é a mesma para qualquer sequência de n coordenadas. Então, essa é a propriedade que a gente chama do processo estacionário. Processos I e D, cadeias de Markov iniciada pela medida invariante, tem essa propriedade. Outros tipos de processos sob certas condições, como processo de renovação, regenerativo também, enfim. E aí, como a probabilidade aqui de acontecer a palavra não depende da coordenada em que ela vai acontecer, a gente vai usar essa notação P de A para a probabilidade da ocorrência da palavra A, né? Certo? Bom, uma outra notação que a gente vai usar é o conjunto das palavras que tem probabilidade positiva, porque às vezes numa cadeia de Markov como entrada 0 na matriz, a gente pode ter uma palavra que não tem probabilidade positiva, né? Então, aqui a gente vai trabalhar com esse conjunto, e pegando palavras com probabilidade de ocorrência positiva, a gente vai usar esses dois símbolos aqui, que um subscrito A vai significar a probabilidade da ocorrência de um evento, dado que a palavra A aconteceu nas primeiras n coordenadas do processo. Isso significa, dado que a gente partiu da palavra A, qual é a probabilidade de acontecer tal evento. E mesma coisa para a esperança de um evento condicionado a A. Tá? Então, essa é uma notação que a gente vai usar aqui. Bom, e aí a gente define o tempo de entrada de forma mais formal aqui como sendo o ínfimo das coordenadas em que o A aparece a primeira vez, é o que eu falei lá no começo, só que escrito aqui de forma mais formal, dado uma sequência. E existe uma outra quantidade nessa área que a gente trabalha que é de muito interesse, que é o tempo de retorno. O tempo de retorno é exatamente a variável aleatória do tempo de entrada, é o TA, condicionada a processos que começam a partir da palavra A. Então, o tempo de, como o próprio nome diz, né, é o tempo que demora para, já que você saiu de A, quanto tempo demora para você retornar para A. E aí, um resultado clássico que dá nome aqui a essa apresentação que eu estou fazendo é o lema de K, que ele foi considerado o primeiro resultado quantitativo nessa área de tempos de entrada e retorno, que ele diz que o tempo de retorno esperado, o tempo de entrada, dado que você saiu da palavra, ou seja, o tempo de retorno esperado, ele é igual ao inverso da probabilidade da palavra. Ele usa como hipótese que o processo tem que ser estacionário e ergódico, mas ergódico é uma classe bem geral de processos que inclui os mais variados tipos, inclusive todos que eu mencionei agora há pouco. Então, ele tem essa fórmula que é bastante intuitiva, inclusive, né? Quando a probabilidade de um evento é pequeno, o tempo de retorno esperado é maior, então, bastante intuitiva. Só que ele obteve essa fórmula, ele não usou a expressão da distribuição do tempo de retorno, porque, como eu falei agora há pouco, a gente não tem uma expressão explícita. Ele usou propriedades dos processos estacionários e ergódicos para obter essa fórmula. E, naturalmente, tentou-se obter uma fórmula usando os mesmos métodos para a esperança do tempo de entrada. Quanto tempo demora para a palavra entrar em média, e não retornar. Mas essa tarefa não teve sucesso, não conseguiram usar o mesmo método do tempo de retorno para a entrada. E também, como eu disse agora há pouco, a gente não tem uma fórmula para distribuição do tempo de entrada que poderia ser usada para obter o tempo de entrada através da integral. Então, uma coisa que tem sido feita nas últimas décadas é obter uma distribuição aproximada para o tempo de entrada e retorno também. Nas últimas décadas tem se mostrado que a melhor aproximação, melhor distribuição, que melhor aproxima a distribuição dessas duas variáveis é a distribuição exponencial. E aí, se a gente olhar para o lema de CAC, né, o que ele sugere? Ele sugere que, já que eu vou usar uma exponencial para aproximar a distribuição do tempo de retorno, o parâmetro tem que ser PDA, probabilidade da palavra A, por causa da esperança. E a gente também pode conjecturar que isso também poderia ser uma boa aproximação para o tempo de entrada, né? Então, essa seria um primeiro palpite. Bom, aí a partir do paper do Galvis e Schmidt, em 97, mostrou-se para que, sobre uma determinada classe de processos, na verdade, a melhor distribuição exponencial que aproxima, para você conseguir aproximar para qualquer palavra, você precisa usar não só PDA como parâmetro, mas um outro fator de correção, que eu estou representando por lambda aqui, que ele depende de algumas características da palavra A, depende da própria palavra A. Então,
Ele voltou. Pode vir.
pode ir? Tá.
Uhum.
Então, como eu estava dizendo, outros trabalhos vieram depois desse de 97, mostrando, obtendo outras aproximações de tempo de entrada e retorno com outros parâmetros de correção no lugar do lambda, melhores termos de erro, aumentando o número a classe de processos para os quais isso vale. Então, tiveram vários resultados. Mas, desses resultados, só um momento, desses resultados que vieram depois, eles ainda tinham dois problemas quando a gente tem como objetivo obter uma aproximação para a esperança do tempo de entrada, que é isso que a gente está buscando, né? Um lema de CAC para o tempo de entrada. Duas questões ainda continuaram sendo problemáticas nos últimos trabalhos, né? Ainda não tinham sido resolvidas, que são o termo de erro da aproximação exponencial, ele precisa decrescer em T para que a gente consiga obter a esperança do tempo de entrada através da integral, da distribuição da cauda, porque se o termo de erro for constante, como era do trabalho do Galvis, que eu mostrei agora há pouco, se ele for constante em T, a integral vai dar infinito, então você não vai obter aproximação nenhuma. Então, ele precisa ser um erro que decresce em T. E a outra coisa é que os parâmetros de correção, lambda, que foi usado naquele paper que eu falei, e outros, em geral, eles eram parâmetros não intuitivos e difíceis de calcular. Eles dependiam da própria distribuição do tempo de entrada. Então, se você quer obter uma aproximação da esperança do tempo de entrada, você precisa de um bom lambda, porque o PDA, em geral, é fácil. Você tem os parâmetros do processo, você consegue. Agora, você precisa de um lambda bom para obter isso. Então, juntando esses dois problemas aqui, né, nenhum dos dois trabalhos, os trabalhos anteriores, alguns tinham um parâmetro muito bom, só que não tinha o termo de erro desejado e vice-versa, né? Então, juntando essas duas questões aqui, no ano passado a gente publicou um paper aí que eu vou pôr a referência no final, o nome completo dele no final, em que a gente obteve uma nova aproximação para o tempo de entrada, uma nova teorema de aproximação, que ele resolve esses dois problemas que eu mencionei. Ele tem um termo de erro que decresce Ele converte para zero conforme o tamanho da palavra vai para zero, o n vai para... Desculpa, conforme o tamanho da palavra vai para infinito. E ele também converte para zero com t exponencialmente rápido. Além disso, esse teorema ele usa no lugar do lambda um outro parâmetro chamado post potencial, que eu vou falar um pouco mais dele daqui a pouco, que é um parâmetro muito mais fácil de obter, inclusive ele tem significado intuitivo, é fácil de entender. Então ele resolve esses dois problemas. Só fazer uma observação aqui, se vocês olharem nas hipóteses, aí ela exige que o processo seja psi-mixing ou phi-mixing. Essas duas condições são condições clássicas de mistura, são medidas de dependência de longo prazo. Eu não vou entrar em detalhes aqui sobre elas, mas elas incluem processos ID, cadeias de Markov infinitas, sob algumas condições também, cadeia de Markov infinita, processo de inovação, elas incluem uma classe bem grande de processos. Bom, dito isso, vamos voltar aqui. Aí, aplicando esse teorema, então, a gente consegue obter esse corolário aqui, que ele te dá uma aproximação para o tempo de entrada, para a esperança do tempo de entrada, mas não só para o primeiro momento, mas a gente consegue para todos os momentos do tempo de entrada. A gente mostra, inclusive, que esses momentos são finitos, e nas mesmas condições do teorema, a gente tem essa aproximação. Qual o significado disso? Esse termo de erro vai para zero, esse epsilon, conforme o tamanho da palavra cresce, né? Então, o significado disso é que a gente tem essa expressão, uma aproximação para o tempo, para os momentos do tempo de entrada, para qualquer momento do tempo de entrada, dependendo da probabilidade da palavra e desse parâmetro ρ, que eu vou falar dele ainda. Então, reparem que esse seria uma espécie de lema de K assintótico, né? Porque a gente depende que o n seja grande, né? Para n ficando cada vez maior, mas ele te dá não só a esperança, mas te dá todos os momentos, uma aproximação para todos os momentos. Reparem que essa expressão é exatamente a expressão dos momentos da distribuição exponencial com parâmetro P de A vezes ρA, né? Bom, vou falar um pouco do parâmetro para mostrar para vocês por que esse parâmetro é importante aqui no nosso contexto, do posto de potencial. Para isso, eu vou definir primeiro uma outra quantia chamada primeiro retorno possível, que é o tal de A, né? O tal de uma palavra A, o primeiro retorno possível, ele é o primeiro tempo em que a palavra pode retornar com probabilidade positiva. Vocês vão ver que nem sempre ela pode retornar logo de cara, nem depois de 3 passos. Com probabilidade positiva, ela pode retornar a partir de um certo tempo. Esse primeiro retorno possível é o tal de A. E o posto de potencial, que é o nosso parâmetro, ele é definido como a probabilidade do primeiro retorno acontecer depois do primeiro retorno possível. Então, que a gente não retorna no primeiro retorno possível, mas depois disso, tá? Então, esse é o nosso ρ. Quando eu fizer o exemplo aqui, vai ficar claro como que ele funciona. Eu vou mostrar também que ele está relacionado, esse ρ, às propriedades de sobreposição da palavra. Como ela se sobrepõe. Além disso, ele tem um significado intuitivo, um significado até físico, que eu vou deixar nas referências aqui, os artigos que vocês podem entender um pouco melhor disso, eu não vou entrar em detalhes sobre isso. Então, voltando para aquele nosso exemplo do processo ID sobre o conjunto ACGT, vou denotar aqui por PA a probabilidade de acontecer o símbolo A em qualquer lugar, porque é estacionário, e PC a probabilidade de ocorrer o símbolo C. Tá? Considera agora, só para a gente entender como funciona assintoticamente, 2 sequências infinitas de símbolos, desses símbolos que podem ser realizados por esse processo. A sequência AC, 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 AC periódica, e uma sequência que é não periódica, a gente chama de aperiódica, começa com A e depois continua C, 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 C sempre. Tá? E aí, se a gente olhar os N primeiros símbolos dessas 2 sequências, da sequência A e da sequência B, observe o seguinte, na palavra A, quando você começa um processo partindo dela, você pode retornar à própria palavra apenas 2 passos depois. Não importa qual o tamanho do N, qual o tamanho da palavra. 2 passos depois você consegue retornar, porque basta recolocar os dois símbolos que estão faltando para completar a sequência AC, AC, AC. Então, o primeiro retorno possível, ele acontece logo de cara, porque a palavra ela tem uma grande sobreposição. O que não acontece com a palavra B. O primeiro retorno possível é só depois que acabar a palavra. Você não consegue retornar, né, dentro da própria palavra, porque você precisa de um A, e não tem nenhum A na palavra. Né? Então, usando essas informações, a gente consegue com muita facilidade calcular os parâmetros, o ρ de A e o ρ de B, que no caso do A, ele vai ficar, a partir de n igual a 2, ele fica constante, igual a 1 menos PA PC, porque é 1 menos a probabilidade de você retornar logo de cara. Retornar logo de cara é colocar o A e o C. Então, a posse de potencial da palavra A, ele é positivo, menor que 1, e fica constante assim sempre. Da palavra B, é 1 menos a probabilidade de você retornar ela logo depois que acaba a palavra. O primeiro retorno possível logo no final da palavra, que é justamente a probabilidade de ocorrer a própria palavra. E como ela tem n símbolos, conforme n cresce, essa probabilidade vai para 0, ou seja, o posto de potencial vai para 1. Ele converge para 1. Então, são dois parâmetros bem fáceis o parâmetro de potencial é bem fácil de obter, é só você olhar o primeiro retorno possível e a probabilidade de não retornar nesse primeiro retorno possível. Ainda falando desse exemplo, a gente pode ver que, no caso da palavra B, a distribuição do tempo de entrada é exponencial, é aproximadamente exponencial de parâmetro P de B, porque o ρ vai convergindo para 1. Né? No caso da P de A, o ρ não converge para 1, então a gente tem uma aproximação melhor usando o ρ. Tá? Uma outra questão aqui importante. Conforme o ρ vai convergir para 1, então o tempo esperado para a palavra B reaparecer, aliás, desculpa, aparecer a primeira vez, é aproximadamente o inverso da probabilidade B, que pelo lema de cá, que ele é o tempo de retorno, ou seja, o tempo de entrada esperado se aproxima do tempo de retorno esperado, da esperança do tempo de retorno. No caso da palavra A, a aproximação envolve o ρ, né, o inverso de PA vezes o ρ, como a gente já falou. Não é o tempo de retorno esperado, mas é da mesma ordem, porque, como eu mostrei no slide anterior, o ρ ele não vai para 0 quando o n cresce, ele fica um número positivo constante. Então, apesar de não ser a probabilidade, não ser igual ao tempo de retorno, é da mesma ordem, né? Bom, e aqui eu coloquei aqui essas duas expressões para mostrar para vocês que o cálculo dos momentos fica bem simplificado com o corolário que a gente mostrou. Você consegue obter fórmulas explícitas que aproximam bem os momentos do tempo de entrada, tanto de A quanto de B, né? Bom, só que aí tem uma outra questão aqui que é importante sobre o ρ. No caso que a gente mostrou, os dois exemplos, o ρ ele é positivo. Um converge para 1 e o outro fica positivo para sempre. Nesse caso, os momentos do tempo de entrada, eles têm a ordem de 1 sobre a medida elevada a beta. No caso de beta igual a 1, 1 sobre a medida. Porque se o ρ é positivo, então, conforme n cresce, fica de uma ordem de uma constante o ρ, só a medida que vai crescendo e o tempo de entrada vai crescendo, a esperança, né? A medida vai diminuindo, a probabilidade da palavra vai diminuindo e a esperança vai crescendo. Então, eles mantêm a mesma ordem de grandeza. Uma outra coisa é que quando você tem a convergência do ρ para um número que fica entre 0 e 1, você sabe, então, já que eles são da mesma ordem, né, você sabe que a probabilidade, quer dizer, um é a ordem do inverso do outro, a probabilidade da palavra elevada a beta vezes multiplicado pela esperança do momento do tempo de entrada converge para uma constante, quando o ρ converge. Então, isso te dá uma aproximação mais precisa ainda, porque você sabe para onde que o ρ está indo. Então, são duas questões importantes, quando o ρ converge ou não e a positividade. A gente tem alguns tipos de processo, existem tipos de processo que não são phi-mixing, por exemplo, processos de renovação ou cadeia de Markov infinita sob certas condições, em que pode ocorrer do ρ convergir para 0. E aí a gente tem uma mudança de escala. Por que uma mudança de escala? Porque os momentos do tempo de entrada vão ser muito maiores do que os momentos do tempo do que o inverso da medida elevada a beta, da probabilidade da palavra elevada a beta. Isso a gente consegue mostrar, em particular, isso significa que a esperança do tempo de entrada é muito maior que o inverso da probabilidade de A. E esse inverso da probabilidade de A é a esperança do tempo de retorno. Ou seja, quando o ρ vai para 0, a ocorrência, o tempo médio para ocorrer a entrada é muito maior, é de uma ordem muito maior do que o tempo médio para ocorrer o retorno. Então, o comportamento assintótico do ρ importa para a gente. Por isso, a gente também tem um outro resultado nesse mesmo paper que eu mencionei, que mostra que, primeiro, se você está dentro da condição phi-mixing, o ρ converge para 1 quase certamente. Então, para quase todo ponto que você pegar, você vai ter a convergência para 1. E a outra é que, mesmo se não convergir para 1, você tem, sob essas condições aqui de mistura, você tem a garantia de que o ρ ele é limitado por baixo por uma constante. Qualquer palavra que você pegar, e para qualquer n, você tem n suficientemente grande, você tem uma quantia positiva, você tem um limite positivo para esses ρs. Ou seja, isso impede que o ρ se aproxime de zero e dê aquele problema de mudança de escala que eu falei no slide anterior. E aí também a gente pode concluir que, para realizações típicas do processo, a distribuição que melhor aproxima vai ser, já que o ρ converge quase certamente para 1, a distribuição que melhor aproxima é, de fato, a exponencial com parâmetro P de A. Então, tem essas consequências, né? Então, como também consequência desse teorema e do corolário anterior, a gente pode concluir duas coisas aqui que são diretas do corolário anterior, que, ao contrário de quando o ρ converge para zero, nesse caso aqui a gente tem quase certamente o produto da probabilidade de A vezes o tempo esperado ou dos momentos, no caso, converge para gama, né? Uma constante em função de beta, mas em relação a n constante. E também aquilo que eu estava mencionando no exemplo lá, que os momentos vão ter a mesma ordem do inverso da medida da probabilidade da palavra elevada a beta. Né? Em particular, se a gente toma beta igual a 1, então, sob as condições do corolário, a gente tem essa convergência esperada, quer dizer, o que a gente espera, né? Que quase certamente a probabilidade de A vezes a esperança de A converge para 1, que acontece no caso do retorno, né? Constante igual a 1. E mesmo quando não converge, mesmo quando você está nas realizações não típicas do processo, eles têm a mesma ordem de ocorrência, o tempo de entrada e esperado e o tempo de retorno esperado. Tá? Então é isso, a gente queria apresentar aqui como que a gente pode avaliar os momentos, em particular a esperança do tempo de entrada em comparação com o resultado clássico do tempo de retorno. Tá? Aqui são algumas referências, a primeira é um artigo que eu mencionei, e depois a gente tem outras referências com revisão de resultados históricos, e, bom, acho que é isso. Obrigado, estou aberto a perguntas.
Obrigada, Vitor. Então, lembrando, quem tiver alguma pergunta para o Vitor, pode escrever a pergunta diretamente no chat ou indicar para que a gente possa abrir o seu microfone e você fazer a pergunta para o Vitor, ou pode levantar a mãozinha também. Tá? Vitor, eu não sou tão familiarizada com esses resultados. Me diz uma coisa, naquele teorema clássico, já vou liberar para você, naquele teorema clássico, também para tempo de retorno, ele vale para quando você tem processos alpha mixing, esse phi mixing ou qualquer tipo de processo, como que é?
Ele precisa ser ergódico. É porque quando a gente fala nas misturas, tem uma escala, tem uma hierarquia, né?
Uhum.
Que a mistura mais forte de todas é a psi, que você tem o independente, né? Que é o I e D, que é o mais forte, daí você tem a psi, e aí vai indo na escala, né? Aí tem um tipo de mistura que é o alfa, que você mencionou, que cadeias de Markov são pelo menos, na verdade é um estágio antes que a beta, mas são pelo menos alfa, mesmo que elas sejam infinitas. E processos ergódicos, na verdade, eles englobam todas essas misturas. Então,
então é muito mais forte, é bem mais abrangente.
Muito mais geral, muito mais geral.
Tá.
Tem processos... a condição de ergodicidade, ela é simplesmente que o processo ele não fique... No caso de cadeia de Markov, para ficar mais claro assim, esse é periódico. E não é bem isso, mas seria como se fosse periódico, que ele não conseguisse ficar preso num certo subconjunto do espaço. Ele vai espalhar por todo o espaço, mais ou menos isso. Mas tem uma definição formal para isso.
Tá. Não, era exatamente isso que eu não tinha entendido. Se esse resultado por tempo de retorno, se ele era mais geral, mais abrangente, né, do que...
Sim, sim.
Tá.
Ele é um dos mais gerais que tem nessa área.
Entendi. Então, acho que a gente pode abrir o microfone do Lambert, né, do Rodrigo.
Vocês estão me vendo aí, me ouvindo aí? Vocês precisam me ver também? Ó, pronto.
A gente quer te ver, Rodrigo.
Que isso? Se ninguém tem me visto ultimamente, né?
Então,
Tá bom.
exatamente.
Bom, valeu, obrigado, Andressa. Vitor, primeiro queria falar que você apresenta bem, cara. Gostei da sua apresentação. Legal. Então, tem um monte de pergunta, na verdade. É o seguinte, primeiro vocês têm um resultado que vocês provam que me corrija aí se eu estiver falando besteira, por favor. Que o tempo, o hitting time médio, né? Que é o tempo da primeira aparição do cara, né? Em geral, é bem maior do que o tempo de retorno médio. Uma coisa assim que vocês falaram, não é? Ou não?
Na verdade, isso, sobre as condições que eu coloquei aqui, isso não acontece. Ele é da mesma ordem. Isso vai acontecer quando esse parâmetro ρ que eu falei, quando ele fica arbitrariamente próximo a zero. Não precisa nem convergir para zero. Se o lim-inf dele for zero, já é o suficiente para que o tempo de entrada, você tenha uma mudança de escala, né? Porque conforme o ρ vai para zero, aquele parâmetro ρ vezes mi, os dois vão para zero, então a escala não é mais o inverso da probabilidade do ρ vezes mi, eu falei mi. O ρ vezes a probabilidade de A, a escala não é mais só o inverso da probabilidade, é o inverso também de outra coisa que vai para zero, que é o ρ. Quando a gente está em condição de psi-mixing e phi-mixing, no caso do phi somável que a gente precisa, na verdade, isso não acontece. A gente tem a garantia, mostrei aqui, a gente tem a garantia de que eles são da mesma ordem. Não necessariamente, você pode ter o tempo de entrada maior, o tempo médio de entrada maior que o tempo médio de retorno, mas é maior multiplicado por uma constante. Então, conforme ele cresce, eles ficam da mesma ordem. Essa é a questão.
Tá, justamente essa que é a minha segunda pergunta. Entra aí. É o seguinte, então, é porque você define esse parâmetro ρ de A como sendo a probabilidade do tempo de retorno ser maior do que o mínimo tempo de retorno, né? Isso é uma coisa meio, digamos assim, né? Intuitivamente falando, esse negócio tem que ir para 1 e tal, sob condições razoáveis, porque se a gente lembrar que esse cara é o ínfimo de todos esses outros ali, né? Então a gente espera que o ínfimo de um conjunto seja menor do que os outros termos do conjunto. Ou eu estou falando besteira aqui também?
Assim, a gente tem a prova de que ele vai quase certamente para 1, mas tem certos pontos periódicos em essência, que ele não vai para 1. Ele pode, no caso de ID e Markov, ele converge para um número positivo. O processo de inovação também, exceto o ponto todo zero. Mas tem processos em que ele pode convergir para zero, mas assim, a gente tem uma condição que eu não coloquei aqui também, sobre processos alfa. Se a taxa do alfa for menor que 1 sobre n quadrado, a taxa que o alfa vai para zero, também o ρ vai quase certamente para 1. Então, até onde a gente tem todos os indícios aqui, talvez isso valha. E vale também se valer a condição de especificação para processos ergódicos, que eu acho que você conhece, que você tem um artigo nisso, quando tal A sobre N converge para 1, né, quase certamente, o ρ também vai para 1, nesse caso. Então, todas as evidências que a gente tem é que, por mais geral que seja o processo, o ρ vai convergir quase certamente para 1. O problema é que tem pontos específicos em que ele pode ir para zero ou pode não convergir, inclusive, tem exemplo de que ele fica alternando, ou pode convergir para um número positivo.
Tá, não, então, agora é porque eu fico um negócio meio técnico aí, eu não consigo entender nada, né? Eu queria fazer umas perguntas menos técnicas agora, tipo, dá pra gente chutar, assim, intuitivamente que essa história de que naquele caso do seu exemplo que você deu, esperança do tempo, quer dizer, o tempo médio de primeira aparição é bem maior que o tempo médio de retorno, dá para dizer uma coisa tipo, cara, se o cara já apareceu na minha realização do processo, então eu tenho um ambiente favorável para ele aparecer de novo, uma coisa desse tipo? Ou não?
Não, pelo contrário, isso é um pouco até, talvez possa ser contra-intuitivo, mas não. O que você tem é que, nesse exemplo que eu dei, que é I e D, ou mesmo em outros exemplos que não precisa ser I e D, você tem que, para uma realização típica do processo, entrada e retorno tem o mesmo tempo esperado. Por mais que isso possa parecer, não sei, pode ser não intuitivo, porque você saiu da palavra, isso favoreceria você não voltar a ela tão cedo, porque você já saiu dela. Mas, na verdade, quando o rho converge para 1, o tempo esperado dos dois converge para o mesmo valor. Quer dizer, os dois é o inverso da probabilidade da palavra. Então, não, é a mesma ordem, né? O mesmo tamanho.
E é se somente se? Oh, desculpa, Andressa, eu já vou terminar, tá?
Em que...
Quando o rho vai para 1, você tem isso? Se somente se? Ou é tipo, vocês não provaram isso?
Eu acredito que seja uma consequência direta desse corolário aqui. Esse aqui, né? Se o rho vai para 1, se você tomar beta igual a 1 aqui, entrada e retorno, só que assim, sob essas condições de mistura, né? A gente não tem, para cima dessas condições não temos, mas sob essas condições, sim, quando o rho vai para 1, entrada e retorno vão ter aproximadamente o mesmo tempo médio.
Tá. Bom, desculpa, gente, perguntei demais. Valeu, obrigado.
À vontade. Obrigado, Rodrigo.
Valeu.
De nada, Rodrigo, tá ótimo. Pode voltar nas outras palestras, sempre bem-vindo. É isso,
Valeu.
então. Obrigada novamente, Victor, pela apresentação, excelente apresentação.
Agradeço.
Obrigada. Então, pessoal, lembrando que nós voltamos amanhã com um mini curso do professor Peter Miller às 10 horas da manhã e depois com mais sessões na parte da tarde. Então, nos vemos amanhã.